In the previous, welcome back to day 2, involving limits involving infinity this time. We looked at limits earlier as x approaches a value, but this time we want to look at what happens if the variable's approaching infinity. Before we do, I wanted to first take a look at, we saw that the limit of sine x over x as x approaches 0 was 1. And we saw a graphical way of looking at that by graphing cos x and the line 1 and seeing that sine x over x got sandwiched in between the two. We're now going to take a look at how to do this algebraically and geometrically. First, let's consider the area of, so this is the unit circle, right? The radius is 1. And we want to first look at the area of triangle MOA. Well, before we can do that, we're going to need the height. And the height would be this line right here. But relative to that angle x, that's just the sine of x. Right, the sine of x. Right, opposite over hypotenuse, and the hypotenuse in this case for the triangle MOA anyway, this is just 1 because that's the radius of that circle, being a unit circle. All right, so the area of MOA, this would just be 1/2 the base, 1/2 the base, and the base, this base over here is 1 because the radius is 1. So 1/2 the base times the height, which is that red line. So that's just sine x. And so this ends up being sine x over 2. Next, we're going to take a look at the area of the sector MOA. Well, the area of the sector, we'd have to figure out what fraction x is, that angle is of that whole entire circle, which is 360 degrees or 2 pi. So that fraction would be x divided by 2 pi. Now we would multiply that by pi r squared. So pi, the radius we said is 1 squared. And so this just comes to the pi's would cancel. And so we end up with x over 2. And if we take a look at the area of triangle NOA, N being the extension of the radius here from O to M, in that triangle, which is also right angled, the height, this height right here, this would just be the tan of the angle x, right? The tan of x is opposite side, which would be this height divided by 1. So the tan of x, so the area of triangle NOA would be 1/2, I can do this in black here, is 1/2 the base, which is 1 again, times the height, which is tan x. And so this ends up being tan x divided by 2. Now, you can tell from the picture that the area of triangle MOA is less than or equal to the area of the sector MOA, which would be less than or equal to the area of NOA. Right, just looking at the picture. Well, now we can substitute all the values we found. The area of triangle MOA, that was just sine x over 2. So that would be less than or equal to the area of the sector, which is x over 2, which would be less than or equal to the area of NOA, which was tan x over 2. Now, if we were to multiply each of those entities there by 2 over sine x, this turns into 1, would be less than or equal to, this would end up being x over sine x, less than or equal to, and this would end up being 1 over cos x. Now, I can flip all the inequality signs around if I flip the fractions over. So 1 over 1, of course, is just 1. So this would be greater than or equal to sine x over x, which should be greater than or equal to cos x. And now writing it the other way around, cos x then is less than or equal to sine x over x, which is less than or equal to 1. And so this proves what we set out to say, that sine x over x falls between cos x and 1. And we saw in a previous lesson that as x goes to 0, cos x goes to 1. On the right-hand side we have 1, and so sine x over x would get sandwiched in between. So we can, well, you can look at the previous lesson and you can see the limit argument. Anyway, just thought I would show you why this falls between cos x and 1 algebraically and geometrically. Now let's get to talking about limits as x approaches infinity. The notation limit as x goes to plus infinity simply means as x approaches a very large positive number, while as x goes to negative infinity, we say means as x approaches a very large negative number. So now let's take a look at the function 1 over x. I've graphed it on the right-hand side, courtesy of Desmos. And as x goes to infinity, we can see what happens, because as x goes to infinity, that's like going in this direction, we can see that the y value is approaching 0. Likewise, as x is approaching negative infinity, in other words going in this direction, you can see that the graph is also approaching 0. Granted, one of them is approaching it from above and one of them is approaching it from below, but they're both approaching the same value. And we've said in an earlier lesson that if the limits, two one-sided limits, are equal to each other, then we can say that the limit as x approaches infinity of 1 over x is also equal to 0. So y equals 0, we say corresponds to a horizontal asymptote. All right, moving along. What's the limit as x goes to infinity of sine x over x? We looked at sine x over x as x approaches 0 earlier, but now we want to talk about as x approaches infinity. Well, let's first consider what sine x looks like. We know that sine x starts at the origin, well, goes on both directions, but this cycle looks like this, and it just continues like this forever. And let's take a look at considering sine x between -1 and +1. Now, we know that sine x goes between negative and +1. And so if we divided everything here by x, we end up getting -1 over x is less than or equal to sine x over x, is less than or equal to 1 over x. And we've discussed 1 over x earlier. This is 1 over x. And we know that the limit as x approaches infinity, both positive and negative, so I can just write it like this, of 1 over x is just 0. So given that, using the squeeze theorem then, and the same true is for a negative 1 over x, because negative 1 over x would just be the reflection of 1 over x in the x-axis. And so the limit as x approaches infinity of negative 1 over x is also 0. And so the two limits on the other side, on either side there, are both approaching 0. And so if that's true, then the limit as x approaches infinity of sine x over x is also 0. Also 0 because of that. Okay, the fact that sine x over x is sandwiched in between those two. And so using the squeeze or sandwich theorem, we can make that conclusion. Moving along. This particular slide was shown earlier regarding all the properties of limits, but in the context of limits as x is approaching a particular value. But the same thing holds true if the c over here was infinity. So all the properties discussed before regarding finite limits are also true for limits approaching infinity. Now let's take a look at some examples of limits of polynomials and rational expressions. So the first one is the limit of f of x plus sine x. Now using the properties of limits, I can break this up into two and write this as the limit as x approaches infinity of 5x plus the limit as x approaches infinity of sine x. For 5x, as x goes to infinity, this is infinity, and as x approaches infinity for sine x does not exist. And so we would say that this does not exist. Okay, so infinity plus does not exist translates to does not exist. Even if both of them were infinity, if a limit is infinity, we still say it does not exist, because a limit only exists so long as it approaches a finite number. All right, in this case, this using the properties of limits would be the limit as x goes to infinity of 5, that's 5x over x, plus the limit as x approaches infinity of sine x over x. Well, the limit of 5 as x approaches infinity is just 5, because it doesn't depend on x. And we saw in the previous slide that the limit of sine x over x as x approaches infinity is 0. And so this is equal to 5. So I've taken the liberty of, courtesy of Desmos again, of plotting this. So this is 5, right? That's the line y equals 6. This is the line y equals 5. And I plotted this function. That's that one. And as you can see, as x is going to infinity, the graph is starting to approach the line y equals 5. Next, the limit of sine squared as x approaches infinity. Well, because the sine curve undulates like that and goes on forever, using the properties of limits, of course, this is just the limit as x goes to infinity of sine x quantity squared. That's using the power rule of limits. But the limit of sine x as x goes to infinity does not exist. And so this does not exist. Likewise, for the same reasoning, this one does not exist. However, if we take a look at the limit as x approaches infinity of two functions individually whose limits don't exist, this one, because the trig identity, this is the limit as x approaches infinity, and you'll recall that sine squared plus cos squared is just equal to 1 by the Pythagorean identity. And so this is just equal to 1. Next one, the limit of ln 2x. Now, it helps to sort of remember what some of these graphs look like. Ln 2x looks like this, and ln of x looks like this, and the ln of 2x is just a horizontal compression by a factor of a half, and so it would essentially look the same. But as x goes to infinity, you can see that this does not exist. Likewise, using your transformations, this is the ln of x, but the ln of x plus 1 just simply means move it 1 unit to the left, and so it would look like that. And as x goes to infinity, once again, this one also does not exist. Now let's take a look at combining these two functions. So while both of those limits did not exist, look at what happens here. Using the properties of the laws of log laws, or ln laws in this case, this becomes the ln of 2 plus the ln of x minus the ln of x plus 1. That's just using the properties of lns or logs. Then this becomes the limit as x goes to infinity of, and now I can put the ln x minus ln of x plus 1 together using the properties of logs and write that as the ln of x over x plus 1. Now, as x goes to infinity, since the ln of 2 doesn't have any variables in it, that's just ln 2 plus, and then the ln of x over x plus 1, as x goes to infinity, this plus 1 is not going to matter, and so this is just going to behave like x over x, which is 1, so that's just the ln of 1, but that's just equal to the ln of 2, since this thing is just equal to 0. So what is the ln of 2? It's roughly 0.693. I plotted it down here, again, courtesy of Desmos. And looking at that function, you can see as x goes to infinity, in this direction here, the graph is approaching the line 0.693, or ln 2. Okay, let's look at infinite limits as x approaches some value. In the case of 1 over x, which you'll recall looks like this, we talked about what happens as limit of 1 over x as x goes to infinity, but now let's look at as x approaches the y-axis. As x is approaching the y-axis, namely 0, but from the right-hand side, so that's what that notation means, 0 plus, we can see that the graph is taking off and going in this direction as x is approaching 0 from the right. And so this is positive infinity. Whereas the limit of 1 over x as x approaches 0 from the left-hand side, namely from this direction, we can see that y is going to negative infinity. And these are different. And so we say that the limit, so does the limit of 1 over x as x approaches 0 exist? And the answer is no, because they're approaching two different values here. So that's because the y-axis, namely x equals 0, corresponds to a vertical asymptote. How about the limit as x approaches 0 of 1 over x squared? 1 over x squared, or x squared rather, is always positive. And so the graph now looks like this, almost like a volcano going up. And does this limit exist? Well, the answer is no. So the two one-sided limits both do approach infinity. So the limit as x approaches 0 from the right of 1 over x squared is equal to positive infinity, and the limit as x approaches 0 from the left of 1 over x squared is also positive infinity. And you might think, well, since they're the same, we can say the limit exists. But because it's approaching infinity, and infinity is not a number, it's not a finite number, right? It's infinity. And so we say, you don't say it's infinity. So since it's at infinity, which is equal to infinity, we say do not exist, does not exist. The limit does not exist. You might find some things on the internet to the contrary, but this is in fact true. Now let's talk about end behavior. In an earlier math course, certainly in high school, you may have learned about end behavior of graphs. We can see, just so you know which one's which here, the 5x cubed minus 3x squared one, that would be the red one. So this guy here is this. And 5x cubed is the blue one. So this one is the blue one. Now, you want to take a look at what is the limit of f of x as x approaches infinity, namely 5x cubed minus and so on, divided by 5x cubed. Well, we can break this up. We can say that this is the limit as x approaches infinity. And we can divide all those terms by the 5x cubed. So we end up getting 1 minus 3 over 5x plus 2 over 5x squared minus 1 over 5x cubed. Now, as x goes to infinity, i.e. getting very large, these numerators are not going to be of any consequence. And so all of these things all go to 0. And so we end up getting that this limit is just equal to 1. And so we say the limit as x approaches infinity of f of x is equal to 1. You can do it as x goes to negative infinity, and the same thing happens. It'll still be equal to 1. And so the limit is equal to 1 as x goes to infinity. Let's discuss end behavior models for this function e to the minus x plus x. I've taken the liberty of graphing e to the minus x plus x. That's the red graph that you see here, this whole thing. Okay, this whole thing is that. And I've also graphed the line y equals x here, just for comparison. Now, just so you, in case you don't remember, E, which is equal to 2.71828 and so on, is referred to as the Euler constant, named after Leonhard Euler. And probably, besides pi, one of the most famous numbers in constants in mathematics. Now, let's just take a look at the graphs of these functions. 1 over x, e to the x looks like this, like any other exponential function, e to the x. And e to the minus x would just look like this. Right? That's just a reflection in the y-axis. Now, as x is approaching infinity, positive infinity, look at what f of x is doing. That's the red graph. F of x looks like, y equals x. It's approaching the line y equals x in the very short term here. And as x is approaching negative infinity of f of x, it looks like e to the minus x. What's the conclusion of this? Well, what this says is, so y is equal to x is a right end behavior model. Behavior model of f of x. Right? Because that was x going to positive infinity. And this statement, as x goes to negative infinity, says that y equals e to the minus x is a left end behavior model of f of x. Okay, we're just talking about what function it behaves like as x goes to infinity or negative infinity. All right, to continue the discussion on end behavior, we're taking a look now at a rational expression, namely f of x over g of x. So we say the function g of x, i.e. the one in the denominator, is said to be the right end behavior model of f if, you notice this is not a spelling mistake, it's if and only if. Okay, that's what the IFF means. If and only if the limit of that is equal to 1. What does if and only if mean? It means that the statement can be read the other way, namely that if the limit as x approaches infinity of f over g is equal to 1, then we can say g is a right-ended behavior model. So this statement works in both directions. Okay. In other words, if A implies B, B also implies A. So that's what the statement if means, IFF, if and only if. Likewise, if the function g of x is a left-end behavior model of f of x, if and only if the limit of f of x over g as x is approaching negative infinity this time is equal to 1. So now let's take a look at three graphs or three functions. F, which is x plus e to the x, which we just looked at. G of x, just like the line y equals x. And h of x, which is e to the minus x. Let's examine what f of x over g of x is as x approaches positive infinity. Well, that would be the limit of x plus e to the x over x, because remember what f of x and g of x there were. And so this is just equal to the limit as x approaches positive infinity. X over x is just 1 plus, and that would be the limit as x approaches infinity of e to the minus x over x. The limit of a constant as x approaches anything is just the constant. That's one of the limit properties. That's just like the line y equals 1. So it doesn't matter what x is approaching, y is always 1. And in the second case, this e to the minus x divided by x, as x gets infinitely large, the e to the minus x, remember this is just e to the minus x over x. This expression is just like 1 over x e to the x. And so as x goes to infinity, this number on the bottom is getting humongously large. And so this limit is just 0. And so that's equal to 1. And you will recall from the definition up above, so we can say, so y equals x, namely the thing on the bottom, is a right end behavior model. Of f of x. Now, what happens as limit of f of x over h of x as x approaches negative infinity? H of x is just e to the minus x. So this becomes the limit as x approaches negative infinity of x over e to the minus x plus the limit as x goes to negative infinity of e to the minus x divided by e to the minus x, which is just 1. This expression here, this is just the same as writing x times e to the x, right, using your negative exponent law. And so as x goes to negative infinity, that's going to be 0. And the limit of the constant as x is approaching negative infinity is just 1. So that's equal to 1. And so y equals e to the minus x, which is the denominator in that rational expression, is a left end behavior model. Of f of x. Okay, hopefully that made sense. And this concludes our discussion about limits involving infinity. Thank you for watching, and keep watching because other videos will be added as time permits. Thank you and goodbye.